In this polynomial, we're given a 0 and asked to find the remaining zeros. Since the 0 that we're given is complex, we can use the conjugate pairs theorem to determine that the complex conjugate of 3i must also be a 0. Complex zeros come in conjugate pairs. So if one complex number is a 0, its complex conjugate must also be a 0. Before we move forward, let's notice that this polynomial doesn't fit our normal process. Our normal process is to get the p over q list and then compare that to the graph of the polynomial. But if we come over here to the graph and input our function, x to the fourth plus x cubed plus 10x squared plus 9x plus 9, and then come over to the graph, it looks like it might not cross the x-axis at all. If we did go about finding the p over q list, that p over q list would end up being plus or minus 1, 3, and 9, which means the only x-intercepts we would be able to cross-reference with would be in this window, which is from negative 10 to 10. And so in this negative 10 to 10 window, that p over q list doesn't help us at all. Now we know we have a fourth degree polynomial, which means that we are going to have 4 zeros, but it is possible that they would all be imaginary zeros. And if they're all imaginary, we wouldn't cross the x-axis anywhere. However, we can still use synthetic division to divide out the factors that we're given, even though those factors are imaginary. We'll follow the same patterns as before, which is that we'll divide out the factors that generate these imaginary zeros. And in this box, we put the 0 of the divisor, which is the same as the 0 that we're testing. We'll put the coefficients of the dividend to the right of that box, which is 1, 1, 10, 9, and 9. We'll leave a lane of space, and then we'll start with the synthetic division. Now, a quick note here is that when we synthetically divide out one complex number, this quotient is going to be nasty. But if we keep going and then divide out the second imaginary 0, that's when we end up with a meaningful quotient. So we really need to divide both of these zeros out before we get something that looks appropriate. So we start by bringing down the 1, and we multiply on the diagonal, combine down to get 1 plus 3i, and then multiply on the diagonal. So here we're multiplying 3i times the quantity 1 plus 3i. And 3i times 1 is 3i, and 3i times 3i is plus 9i squared. 9i squared is the same thing as negative 9, so we'll change that to a negative 9 before we combine down. So now we're ready to combine like terms, and we get 10 minus 9, which is 1, and then plus 3i again. When we multiply on the diagonal, of course, we get the same thing that we just did. We'll say, again, this is negative 9 plus 3i. And when we combine down this time, the 9's cancel out and we end up with just 3i. Multiply on the diagonal, we get 9i squared. And again, that's the same thing as negative 9, so we'll replace that with negative 9. And then, when we combine down, we get a remainder of 0. And as you can see, this quotient does look terrible. And as I said before, we really need to divide out both of these zeros before that quotient looks like something that we can work with. So we'll go one more time, putting the 0 of the divisor in here, which again is the 0 that we are testing. And then we cycle through this synthetic division one more time. We bring down the 1 to get 1 here. We multiply on the diagonal to get negative 3i times 1 is negative 3i. When we combine down, the 3i's cancel out and we just get positive 1. Again, we multiply on the diagonal. Negative 3i times positive 1 is again negative 3i. Combine down, the 3i's cancel, and we have 1. Multiply on the diagonal to again get negative 3i. And now we can see that when we combine down, we get a remainder of 0, and this time the quotient looks so much better. These are the coefficients of the quotient. So now that we've run through 2 cycles of synthetic division, let's go back up to the polynomial and begin the factorization process. We know that x is equal to 3i is a 0 and x is equal to negative 3i is a 0, which means that x minus the 0 of 3i is a factor, and x minus the 0 of negative 3i is another factor. After dividing both of those out, we ended up with a quotient that has 1 as the leading coefficient. And since we started off with a 4th degree and we divided out 2 factors, this quotient is going to be quadratic and 1 is going to be the coefficient on x squared. Positive 1 will be the coefficient on x, and positive 1 at the end is going to be the constant. Remember, when we have a quotient that's quadratic, we no longer need the synthetic division to help us factor. So let's bring our polynomial down here to clean it up and continue working with it to find the remaining zeros. First of all, we'll say that x minus 3i is our first factor, and we'll write this minus a negative as a plus, so we'll have x plus 3i. And then copy down this quadratic, which, by the way, is an irreducible quadratic. It's not one of our special cases, and it doesn't factor using our AC method because there are not 2 factors of 1 that add to 1. So since it's irreducible, this is where we would want to plug in y is equal to 0 and solve for x in each of these factors, which we do by setting each factor equal to 0 and solving them individually. Of course, we already knew these 2 zeros. The remaining 2 zeros come from setting this irreducible quadratic equal to 0, and in order to solve this, I'm going to use the quadratic formula. The 2 options that we have for solving this are quadratic formula and completing the square. I prefer the quadratic formula. So we have x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a, which gives us the opposite of b plus or minus the square root of 1 minus 4 under the radical all over 2, which yields negative 1 plus or minus the square root of negative 3 all over 2. And when we pull the negative out from under the radical, we get negative 1 plus or minus I square roots of 3 all over 2. So let's clearly state our answer. We have x is equal to plus or minus 3i as zeros, and x is equal to negative 1 plus or minus I rad 3's all over 2. Notice that all 4 of our zeros are imaginary, and that means that we aren't going to have any x-intercepts. So we had to get creative to find these remaining 2 imaginary zeros.